Okay, in basketball, there's something known as March Madness, and this is this big college tournament that happens every year in the month of March. The way it works is the top 64, let's look at the men's March Madness just for example. The top 64 teams start off and they play each other down until they win. Now, within these 64 teams, there's four different divisions, and each of these divisions has 16 teams that, based on their performance that season, are ranked how well people think they might do based on what happened during the season. So a first seed, for example, would be the best pick within that particular region, and the 16th seed would be the last place pick. Of course, these are just picks, and in any given game, anything can happen. So that did happen for the first time in 2018, where a number 16 seed beat a number 1 seed. So these two are always, 16 seed and 1 seed are always paired up against each other in this tournament in the first round. It's kind of a privilege or an honor for the number 1 to play a number 16 seed. And from 1986, the start of this version of the tournament, until 2018, we had never had the case where a number 16 seed beat a number 1 seed, but it finally happened here. And if we look at the so there's four regions. We're going to have every year 4 games where a number 16 seed, so shown in red, plays a number 1 seed. And one thing you could do is see how badly the number 16 seeds have gotten beaten every year. So from 2018, for example, Xavier beat Texas Southern by 19 points. Villanova beat Radford by 26 points. Kansas beat Penn by 16 points. In each case, all we need to do is subtract the score from the number 1 seed minus the score from the 16 seed. In University of Virginia's case, they actually lost against a 16 seed, so it'd be 54 minus 74 to give -20. So we're just looking at the point spread over all these games since 1986. How much did the number 1 seed win by? So this was before the University of Virginia upset in 2018. Notice that the difference here, how much the number 1 seed won by, was always a positive number in every case, and typically the most common was that the number 1 seed would win by between 20 and 24 points there, but they had always won. And if you look at this shape of this histogram, how much they won by every time, you can see it's kind of normal. If you would take the average of all these run differentials, it would be 24.7, a standard deviation of 12.1. And we can actually use that information to answer this question. What's the chance that in a March Madness tournament, a number 16 would beat a number 1 seed? So for a given game where you have a number 16 versus a number 1 matchup, what's the chance that the number 16 seed will actually upset, go against expectations and beat number 1? Well, in order for that to happen, remember we saw that Virginia UMBC had a negative score. In other words, the number 16 won. So anytime you have a negative here, that would mean that the number 16's score in the game was higher than the number 1 seed's score in the game. So in other words, we really just need to ask what percent of the curve here is below 0, because anything below 0 is going to be a negative number, which means that the number 16 seed would have beat the number 1 seed. So another way of phrasing this is, in a normal distribution of mean 24.7, standard deviation 12.1, what percent of that distribution is below 0? So is lying in this little tail right here. So go ahead and pause this video now if you have any idea how to proceed from here. If you don't, go ahead and click through. Don't pause it. This would be the formula that we can use to convert in between any normal distribution, like the one we have here, and the standard normal distribution, also known as the z-distribution. So when we look at this formula, we should be able to somehow get 3 of these 4, then we can solve for the 4th. In this case, we have the mean, 24.7, so we have that number. We have the standard deviation, 12.1, but it's not quite as clear which we have here. As it turns out, when we say we want the percent of the distribution that has a score difference less than 0, that 0 is serving as a cutoff, and that's going to take our value of x here. So this x is either going to be an individual score. For example, if you want to see how your ACT score compared to everyone who took it, your individual score would go there. Or it could be a cutoff, is often another common use of the x. And in this case, we have a cutoff between the positive differences, where the number 1 seed won, and the negative differences, where the number 16 seed won. So that cutoff there, that x value, would be 0. So since we have those 3, we can go ahead and solve for z, plugging in our cutoff, our mean, our standard deviation, and we'd get a z-score of negative 2.04. Another way to say that is, in order for a number 16 seed to beat a number 1 seed, based on the data we have, they would need to have a z-score less than negative 2.04. So that brings us back to our original question: what percent of the standard normal is below negative 2.04? Well, that's where we can move to Table A. We can find a z-score of negative 2.04. Notice we're given the z-score, which means we're given the info in the margins. We're going to use that to find the portion below that z-score. Another thing that could happen would be we would be given a portion below a certain score, use this to then find our z-score. But in this case, we already have that, so let's find negative 2.0, and to pick up that last digit there, we're going to go in the 4 column, the 400ths column, and finding the intersection there gives us 0.0207. In other words, if our z-score is negative 2.04, there's 0.0207. That portion of the normal distribution is below that z-score. If we convert that to a percent, it would be 2.07%. So to answer our question, there's roughly a 2.07 chance of a number 16 seed beating a number 1 seed in any given March Madness matchup. There are some other assumptions we could talk about and whether the game has changed enough from 1986, but this gives you a rough idea of how to use the normal distribution to make a prediction.